This tutorial then covers how to use D flip-flops, right, or the set of lecture notes. We're going to say D is for data, D is for delay. Right. It's often called the data flip-flop because it's based on the data latch. We'll see that the output Q is dependent on the input D. Right. Q next is going to be equal to D on the edge of the clock. Also, D is for delay because it takes one clock cycle to actually then take the input and process it through to the output. So basically, when you use that one clock cycle, you're delaying that one clock cycle time and you're dividing a clock in half. We'll see in an upcoming lesson how we can use D flip-flops as clock dividers. For right now, we want to understand their behavior. Right, so in a previous lecture, we took a look at the D latch. We found that the D latch was level sensitive. It had an enable on it, which we could also refer to as the clock. But that D latch was dependent on the level of the clock. Remember, when enable was a 1, Q in the next state was whatever it was on D. When enable was a level of 0, we didn't change state. Well, with a flip-flop, they're going to be edge triggered, right? So it's going to be on the rising or falling edge of the flip-flop is when the output, the next state, will transition. Right? So we're going to capture that logic level just at a shorter instance in time, right? With the, if it was level sensitive, we'd have a longer instance in time, but then we're more subject to error if we do that. So we use the edges to capture that shorter interval of time, make sure we have a stable reading at that point in time. Right, so the D flip-flop, right, will have two inputs, D for data and C for clock. Right. So you'll see different symbols for them. I'll bring up the quarter symbol. Most of the time, we're only going to see a Q output. We're not going to see a Q not output, just a single Q output. The triangle, when you see the symbol, is the clock. D is for the data. Right. Now, normally this is for a rising edge triggered, right? A falling edge triggered has this little inversion bubble next to it for an inverted clock, right? Falling edge trigger. Right? The way the truth table works, or the behavioral table, is that Q in the next state, so our output Q in the next state, is only dependent on D. So we have two inputs to the flip-flop, right? We actually have D and Q because of the fact of the way the flip-flop is actually wired underneath, right? We have this present state input because we have the feedback here, right? We have our data line here. We have basically our enable or our clock, this triangle here, closing, taking care of this. So Q in the next state will only ever be dependent on D. So here D is a 0, Q next is 0. Here D is a 0, Q next is a 0. D is a 1, Q next is a 1. D is a 1, Q next is a 1. You can see it's independent of what the present state is. But we always just say that the characteristic equation, the D flip-flop, is Q next is equal to D. And it's going to be triggered. It can either be triggered on a rising edge, so the triangle, rising edge of the clock, falling edge, we have the bubble inversion before the triangle, right? Right. This can be made from taking some latches and putting them into a master-slave relationship. So here's a simple look at a master-slave D flip-flop. Remember the D latch, the way we had it configured in a previous lecture when we left off here is, I'm going to go back up, sorry, here. We said that we don't want to latch with a common clock. So the output of this one was triggering the input here, and they shared this common clock. We're going to change this configuration now under flip-flops, right, to actually then come up with this master-slave here. So these are still D latches, right? Let's take a look here. We've got D as an input here. I've got the clock coming in here. But I've got the clock inverted over here on the latch. Well, basically, when the clock is a 0 here, the master is not enabled, meaning whatever the output of Q is will hold its state. So if the output of Q happens to be this value that I labeled Y, that's then the input over here. When this is enabled, this output, Y, will transition through to Q. Right. Now, when the clock becomes a 1, in this case, this master circuit is enabled, the slave is disabled. So now the output Y here can become the transition sorry, the next state can be whatever's on D. So Y is going to be equal to D. Q will not change its state. But we can use latches then to make flip-flops. We put them in sort of this master-slave configuration, but then they don't have a common clock because see how this is the inversion of the clock. So that takes care of the problem we had with the different levels and the D input changing and the timing of this output changing and becoming the input to here. So they got rid of that problem. So we'll see that a change in the output of the flip-flop can only be triggered by and during the transition from the clock from 0 to 1. We come up with this sort of arrangement, right? And that becomes the edge trigger that we're referring to. All right, so we're not going to draw out something that looks like this, right? Sorry. This positive edge triggered flip-flop once again goes back to the set reset latch, right? We end up with a clock coming in here. This is all made out of NAND gates. You can see we have a few more gates here. Then feeding back, we have our data latch down here. Remember, our problem with SR is that the 1-1 with the NAND gates caused an indeterminate state. It caused Q and Q not to be the same value, right? Well, with this configuration then eliminates that problem. Sorry for the delay, dog wanted out. Let's take a look then at the D flip-flop state table. We have the input D, right here, its value in the present state. We have Q, and if it's a rising edge triggered, normally we don't show the clock. Here I'm just trying to show that on the rising edge, if this is a rising edge triggered, the Q next will be equal to D. And here D is a 0, Q next is equal to D. In both these cases, D is a 0. And on the rising edge, when D is a 1, right, Q next is a 1. On any sort of non-rising edge, right, it doesn't matter then what D is, there'll be no change in the output, it'll hold its value. So on the level, on the falling edge, right, 1 level, 0 level, falling edge, no change. Only on the rising edge if it is a rising edge triggered flip-flop. Right, we'll actually then program this into Quartus and see the behavior as well. Here's how the flip-flop then operates. Let's look, starting on the left, this is time t equals 0. D happens to be a 0. I'm saying that Q is a 0 at this point in time. Here is the clock signal. At this particular point in time, the clock transitions from low to high. So this arrow indicates the rising edge. It's rising from 0 to 1. Notice here, this is our symbol. This is a rising edge triggered flip-flop. There's no inversion here on the clock. So at that point, then, the output Q transitions to whatever is on the input, D. And right here at this point in time, D happens to be a 1, so notice Q becomes a 1. Right? Now, there is no change in the output Q because even though D is oscillating here, it's going from 0 to 1 during this time, the only change that ever occurs is on the rising edge of the flip-flop. So Q is going to hold its state, hold its state, hold its state till the next rising edge of the clock. Here's my rising edge of the clock here. At this point in time, D happens to be a 0, so the output Q becomes a 0. The point is, right, the output Q only changes on the rising edge. It doesn't matter what's happening on D during that time. If there's no rising edge, then there's no change in the output. It's going to hold its state. Now, flip-flops are different than latches. Right? With a latch was level sensitive, meaning the latch output Q was whatever was D, so Q next equals D, whenever the clock is a 1. So here, let's take a look. Clock starts out low, D starts out low, Q starts out low. As long as the clock is low, it doesn't matter that D goes high for the latch. Finally, when the clock goes high and D is high, the output Q goes high. Notice while the clock stays high and D goes low, the output Q goes low. Now, when the clock level goes low, right, Q will hold its state. It won't change state. It can't change state until the enable level goes high. Well, at this point, then the clock or the enable level went high right here. D happened to be a 1, so Q went back to 1. The whole time this was high, D was high, so our signal stayed high. When this falls low, then Q holds state. Doesn't matter what D is doing. It isn't until the clock goes to a high level again here that our output Q then mirrors D. D happens to be low, so Q becomes low. So remember, latches are sensitive to the level being a 0 or 1 of the clock. Flip-flops are sensitive to clock edges. Well, if this is a rising edge triggered flip-flop, let's take a look. See, both of these are starting out the same. Clock is 0, D0, Q0, right? So this input of D and clock, these two patterns are the same on both of these. So D goes to a 1, Q holds its state until a rising clock edge. So at this instant in time on this rising edge, D happens to be a 1, so Q becomes a 1. Right. Now, see right here where D transitions back down to 0? For our latch, that made the output Q go back to 0 because a latch is driven by the clock level of 1. But on our flip-flop, Q does not change. Q will hold its state until its next rising clock edge, which is here, in which case D happens to be a 1, so Q next is going to be a 1. And again, it will hold its state until the next rising edge. At the next rising edge of the clock, D happened to be a 0, so now Q transitions to a 0. So you can see that even though the clock and D are the same signal of both of these, the output Q is different. The difference being Q only changes for the flip-flop on the rising edge. On a latch, it's level sensitive, whether the clock is a level of 0 or 1, because the clock is that enable signal. So that's the difference between the two. We're primarily going to work with flip-flops, the edge-sensitive devices, in most of the circuits that we'll make for the rest of the semester. Now, before we go into Verilog, let's just go ahead and go over to Quartus. Let's program in one of these and see how it behaves. Right, so I've got a Quartus project up here, right, an empty block. I'm going to insert the flip-flop symbol, so insert symbol. Right. Now, I can just type DFF, right, these are under storage devices. It'll give me a D flip-flop. Right. Let me make that a little bit bigger. All right, now, this is a rising edge triggered flip-flop. It's got the plain triangle. It also has a preset and a reset. We'll talk about those a little bit. Let's just stick with the basic behavior. Here's my input D. I'm just going to wire an input pin to that. I need to get that off of magnification. So here's an input pin here. Here's a clock pin, and we're going to have an output pin of Q. What I'd like to do is I'd actually like to physically wire this to the board. So I'm going to use SW0 because I'm using an Altera DE2 board. I'm going to use then key 0, and key is the push button. Push button 0. So D will be whatever's on my switch. Push buttons are better to use for their edges than the switches. Right, switches, it's harder to detect the edge when you slide them back and forth. Push buttons a little bit easier for you to know where the transition is. All right, and my output Q. All right, I'm going to change that pin name. Let me just go ahead and show that on LED R1. And I'm going to show then, let me put in another output pin. I want to see what the switch state is too. Oh, not input. All right, I'm going to want to see then, let's just always show our value of D right on, or switch 0. LED R, red LED 0. And let me just wire that to that. Okay. I'm going to save this and let's call this D flip-flop test. All right, I need to change the device. I'm going to use an Altera DE2 board. So it's a Cyclone 2, field ball grid array, 672, speed grid 6. So that device right there. I need to import my pin assignments. I had done that in this project. My QSF file for the DE2 is out here. I'll import those. Okay, now, I need to set this as my top level entity because it's a different name than my project. And let's compile. And it'll take a little bit to compile this first one. What we should see, right, is we're going to slide the switch back from its values from 0 to 1. The red LED 0 will show us the switch state. When we program this, bring my programmer. I didn't find my file, which it should be here in my project under output files. The name of my project is flip-flop, so it always names the SOF file the same as my project name. I'll select that. Start the programming here. Let me turn on video, all right, so you can see the board. All right, so here's my DE2 board. I don't have any LEDs on right now. Right, switch 0 is going to be my D input right on our circuit. So you can see when I push it forward, the LED goes on. So switch 0 or D is a 1. When this 0 LED red 0 is off, I know that switch 0 is a 0 and D is a 0. Right, now I'm using these push buttons. Here's key 0. This is going to be my clock. I'm going to have a manual clock. Right, so right now, then I'm going to set D to 1. Notice then my output of my flip-flop is going to be on red LED 1. Right now that state happens to be 0. When I push down the push button, right, and I let go, yeah, I pushed the wrong push button. Right, let me push it, let go. So now that my clock's changed state then, right, when I use that clock. So my push button is acting as the clock. Notice then that my output Q in the next state, or Q, became 1 because D was a 1. Now notice I'm now pushing the clock, so as soon as I change D, the input, to a 0, my output of my flip-flop still holds state. I can go back and forth all I want. My flip-flop won't change its state. The only way it will change is now if D becomes a 0, and I push this button, right, and let go, clock that in, now that's a 0. Once again, I start playing with D, the input. That output of that flip-flop will not change until I push and let go of that button there. Right? So that's how the D flip-flop works as we have it wired. Now there are some preset and reset signals here as well that we can wire up. Let's go back here. We left these blank. Right. Let's see how they work if we wire some more pins in. We need some inputs then. All right. So for preset, and preset is like a set. Fortis calls it PRN. It's just going to be a preset. We should see a 1 coming out of the clock in here. Then we should see, we should see, for clear, a 0. All right. So I can use push buttons for these, or I can use switches. I'm going to make key 2 or key 1. Key 2 will be my reset. Key 1 will be my set or preset. So key 1. Okay. I'm going to save that. I need to recompile because I made changes. No, I don't want to change my programmer. But didn't I wire correctly? Legal name for bus or pin. Which one? Both gave them pin numbers. Let me just run analysis and synthesis. why it doesn't want to tell me which one. I quite understand because it assigned them both. All right. It worked before. Go back to the way we had it before. And that gave no errors. All right. Let's see what I'm connecting wrong. Maybe I should have inverted the key since it's active low. If I use an input. Key 1. Oh, well, I'm missing that bracket. Let me save it. Okay, so I didn't seem to mind that. Let me have the other input here. Not quite sure what I didn't like before. Let's make that key 2. All right. I'm going to compile this. I didn't like that warning. Okay, I'm going to try programming the board. I don't like one of those warnings. You know what? Let me cancel out the last one. Make sure that's still not in there. Start this up. Program it. All right. Now I've got a 1 on my output. Doesn't matter what I'm doing with D. All right, now, what do I have? Let's go back here. So for clear, I get key 2, so 0, 1, 2. All right, so if I press that down and let go, all right, as long as I press that down, notice the output, then I just reset that. Preset, there's preset. All right, so reset, so that's hooked to, or wired to CLRN, clear, right? When I press down key 2, reset then drives the output of Q. So the output of Q is shown on red LED 1. We can see then that becomes a 0, right? Preset, right? Is key 1. I've wired key 1 to that. When I press that, then that causes the output of our flip-flop to be a 1. Right? So the output of the flip-flop's a 1. My switch 0 is a 0. So now if I use the clock, right, and wire this, or press this, right, notice that my output on my flip-flop is a 0. My input D is a 1. Clock, output on flip-flop is a 1. If I want to reset it, press key 2. It doesn't change my value of D. If I want to preset it, key 1 does that. So now you know then what these extra buttons do. Right, so key 1 we wired to preset, which can force us to have an output of 1 on Q. Reset gives us an output of 0 on Q. Right? And so that's the way then the Quartus D flip-flop works. Right? So wire that up yourselves. Right? Play around with it till you get to understand how this works. You don't always have to wire in the reset and preset. As you saw before, when we wired the circuit, we wired it without it. Right, now let's go ahead and see how we would write Verilog for a D flip-flop. Right, let's bring up a new file. All new. All right, Verilog HDL file. All right, so D flip-flop. All right, module. Now avoid naming it DFF since Quartus has something in the library called DFF, so I'll call it D underscore flip-flop. All right, so we have D as an input, we have CLK, clock as an input, and we have Q as an output. These are all single bit signals. So input wire D, CLK clock, output wire Q. Right, we don't show the Q naught as an output. We can always create a Q naught by inverting the output of this. Right, so we've named then our signals in our port list, our input and our outputs. We use then, we have a characteristic equation, but we tend not to use that. We tend to write these with always blocks. Right. Well, we want to come up then with a next state. Right. Q is our next state output. We need to say always at, and it's a clock edge. So if we want positive edge, so we type pos edge and then CLK. At the positive edge of the clock, then we just want to say that Q should be, and I want to use the non-blocking assignment statement with synchronous circuits. So there's my non-blocking assignment statement. Q should be D at that transition. Right. Let's take a look back at our lecture slides. All right. Now there's something else we need to do, right? We need to make this a reg type, the Q. Right? We talked about the fact that whatever goes inside the signal on the left-hand side of the assignment statement needs to be a reg type. Our module needs to look like this. Right? So back here, if I were to save this, let me save it. Remember, I have to name. Right. I have to name the file the same thing as the module name. Make sure I don't want to put in output files. Just want my project flip-flops. All right, now I'm just going to go ahead and make this one the top level. Remove this other one from the project, and let's just do analysis and synthesis. No, don't say my programming tool. That's what it keeps asking me. And look at the error I get. Object Q on left-hand side of assignment must have a variable data type. Well, that's the reg type. Right. So, sorry, here, this needs to have a reg type. So what I need to do is I need to make a reg. I usually call it RQ for register Q. Right. Now when I make this RQ, I also need to drive the signal Q. So I need to assign to Q the value of RQ. So this is like a physical wiring, right? Drive the output signal Q to the reg signal Q. Right. I'm going to say use non-blocking assignment operator with clock-driven circuits. And the other thing is then must use a reg signal on left-hand side of assignment operator. All right, so this has to be a reg type. We have to assign this back. Let's go ahead and see if we could compile this. I'm just going to say no. Yeah, I'm going to change. Save my changes to the Verilog file. Looks like it's going to compile. All right, now it's going to try to place and route, but it really can't do that because I don't. Oh, I'm not downloading it onto the board. I haven't used any hardware signals. All right, let's go back to then this Verilog. Right. All right, that was our simple D flip-flop. We could make a symbol out of it. That's what I did here. I made a symbol out of it. But now we want to add these additional inputs because we just worked then with the Quartus library D flip-flop on the schematic. We saw that it had a preset and a reset. Right? So we want to add those signals to our module as well. So the clear input, its behavior should reset the flip-flop Q right to 0. Preset should set Q to 1. Override has priority, right? So what this means is that the preset and the reset signals are going to override the input. Then they have priority. Anytime we issue a reset or preset, that should take priority to anything coming through on the clock. So asynchronous, clear, and preset. So asynchronous means our reset and preset operation does not depend on the clock at all, right? And it will override both the clock and the D input. Synchronous means that our preset and reset are clear and preset. Then that operation depends on the clock. It's going to be asserted on a clock edge, but it will override the D input. All right. So reset is going to be used to initialize all the flip-flops to 0 upon startup, right? When you power up something, we don't know what state it's in. If we can reset upon power up, then we know what the initial state of all of our flip-flops are, or our digital machines. Think about it. When you first turn on something, you don't want it to be in some sort of unknown state. So when you reboot your computer, what you're really doing is resetting all the circuits in it to correct states. Right? And there are flip-flops in there that you're resetting. All right, so let's take a look then at what our behavior would be. So I'm using then PRN. This is our symbol here from Quartus. PRN was our preset, our set, right? CLRN was our reset. Now, these were actually active low. The inverted bubble here then meant then that you should invert the signal and it will be an active low as opposed to an active high. So we have the following inputs. We have clock, we have D, we have PRN, preset, CLRN, reset. Q next. What this says is we can't assert both signals at the same time. This says here, doesn't matter what clock is, doesn't matter what D is. If preset and reset are both zeros, we don't allow that, right? We can't have two outputs. We can't have both 0 and 1 coming out of there. So we're not going to allow that. In this case, then, if preset is a 0 and reset's a 1, then our output, Q next, will be based on preset. Active low means the 0 is going to trigger this. We'll have the preset. Here now, when preset's a 1 and clear is a 0, active low, then we'll clear this or trigger the reset. So our output Q next will be a 0. Otherwise, when both of these are 1s, when preset and reset are both 1s, then the clock takes over. So if it's a rising edge triggered flip-flop, in this case it is, then on the rising edge of the clock, when D is a 0, Q next will be a 0. Same way here, when preset and reset are both 1s, those signals are not asserted. On the rising edge of the clock, when D is a 1, our output Q plus will be a 1. So Q next is always equal to D. Right? When preset's a 0, right, Q next is 1. When resets a 0, Q next is 0. Right. On the falling edge or on any of the levels, we'll just hold our state. So there will be no state change as long as these remain 1s. Well, it adds some complexity definitely to the circuit, but it gives us ways of generating known outputs out of the circuit, whether we do a preset or a reset. We want to add this then to our Verilog code. All right. So asynchronous, right? Asynchronous means it won't be dependent on the clock at all. But we will use the edge of the reset. We're going to use the push buttons on our board to trigger this. And it's much better to trigger this, once again, the same way we trigger the circuit on a rising clock edge. Well, we want to trigger it on the edge of our other signals as well. And that works really well. The push buttons even better than the slider switches to catch the edge. So let's just go ahead and add the asynchronous reset. Bring Quartus back. Right. So this was just our plain old D flip-flop. Right. Let's go ahead and add an asynchronous reset to it. In order to do that, right, I'd rather just call this signal reset than the Quartus names. It makes more sense to me. That's what I call them all the time. So reset is another input here. All caps, kind of as it looks like I'm yelling. I'm not. Right. So now I can have positive edge clock, or I say I'm going to have neg edge. I'm just using neg edge because I'm going to implement this then with the Altera, and it works really well with the buttons. So neg edge reset. So we said we want reset to take precedence. It's asynchronous. So asynchronous means reset is not dependent on clock. Reset takes priority. So we're going to say if reset equals 0. I'm going to type an integer constant that's 1 bit in size, binary 0. So that's equal to 0. Then I want Q, so RQ, register Q, right, should be set to 1 bit binary 0. Else, the clock must have been asserted. That's our only other choice here. We have this. All right, so that's a D flip-flop. Asynchronous, active, low, reset. And we still assign RQ to Q. We don't change that. In other words, right, if reset active low is equal to 0, then our output Q, or state Q, will be equal to 0. Otherwise, the clock then will trigger this, then RQ is going to be equal to D. So it's a negative edge. Right, negative edge reset can trigger this circuit, or positive edge clock. Either one of these edges can trigger this. But what happens is when we come in, since we check this circuit first, or this condition, if reset's equal to 0, right, we don't perform this action when this is true. We only perform this action. Otherwise, if either one of these edges have triggered this, and this is not true if reset happens to be a 1, a level of 1, well then we're just going to put whatever's on D out to the next state, Q next. Right, so that's how we add in then that negative edge asynchronous reset. If we want to add then an asynchronous active low preset, Q is set to 1, right? Q is cleared. If I want to add that signal in, right, then as well, I'll just call this preset here. Add another signal, input signal here, preset. And we're going to use buttons for this, and so neg edge preset. All right, that edge can trigger the circuit. That belongs in our sensitivity list. Now, it really doesn't matter whether we check for preset or reset first. We have to check for one or the other because they take priority over clocking D through. Right, but we said we're not going to assert both the signals at the same time. So I'm going to say else if preset is equal to a 1-bit binary 0, well then RQ is going to be a 1-bit binary 1, right? We set that to 1. Otherwise, if reset's not low, preset's not low, then we'll put D on through to the output of Q. And that is going to act the same way as this D flip-flop that we used here. Well, let's go ahead and create a hardware level now to test this. A new Verilog, new Verilog file. All right. Hardware level implementation of D flip-flop. All right, so module, I'm going to name a hardware level. Once again, all right, we were using switch 0, we were using keys, and we were using red LEDs for our output. And module. All right, then, all right, we need to, our input, all right, so switches, so 0 down to 0. All right. Input keys, we use 2 down to 0. Our keys, all right. Input, all right, we were using 2 LEDs, red LEDs. And maybe I'll just, those are output. I'm just going to show the push button states on the green LEDs. 2 down to 0. We didn't do that in the other. Just want to show that. This should be output here. All right, output. All right, so now I need to create an instance of this module. We do that here. I like to copy that over in terms of the comments. I know what that looks like. Remember the module we instantiate by using its name. We give it some unique instance number. All right, now I want to wire to D. I want to connect switch 0. Right, to clock, we were using key 0 to clock. Right, and to reset, make that key 1. And to preset, make that key 2. Finally to Q, we were red LED 1 was showing the output of our flip-flop. Let's go ahead and assign then to LED R0. We want to assign switch 0 to that. And now let's assign to our green LED. So when I say LED G, since I made that bus 3 bits wide, if I assign to it key, which is 3 bits wide, we'll see key 2 on LED green 2, key 1 on LED green 1, and so forth. Now, I need to say this. And copy too much. I say that with the same name as the module name. I want to make this the top level. just need this and the flip-flop I've instantiated. You can go ahead and program that. Now, it keeps asking me if I want to save that programmer tool. Right now, let's see. Oop, I made a mistake here. I did not use the double equal sign for comparison. Remember, double equal sign checks equality. Oh, let's fix that. No, I don't want to save that. I should either just save it or, all right, and I didn't pay attention to my case sensitivity. Looks like I need some caffeine, doesn't it? All right, have to spell the signal names the same. And same way there. And my hardware level is not found in the port list. I left it off the port list. I need to pay attention to what I'm doing and not just talk, don't I? If I'm lucky, it'll compile now. If you're lucky, it will compile now. All right, so we were adding these signals from our slide. All right, this is just going through some of what we just did, how these take priority. All right, we'll end here with a D flip-flop after we get it working. The next topic would be a JK, but okay, compilation was successful, 433 warnings. Don't see anything there. Strikes me as a problem. Let's go ahead and program the board. I start the video back up. I turn the board off to erase the last program. I turn it back on. Go ahead and start for the programmer. All right, now let's see what we've got on here. All right, so all of the green LED lights turn on. Remember, these are active low devices, so when the push buttons are not pressed, that will activate the green LED. When I press it, then key 1 is connected to green LED 1. That's turning it off. So active low, depressing, if you think of that as a 1, is going to turn it off. The 0 activates it. All right, so when this is pressed, it's off. When it's not pressed, the green LEDs are on. All right, I'm going to set my switch to 0. Then I said reset with key 1. So if I press key 1 and I go, notice that the output Q shown on red LED 1 is a 0. Right? If I hit key 2 preset, I let go, then we've preset that output to a 1. If I go ahead then and have a 0 on D and hit my clock, press that, then our output of our flip-flop, our next state, becomes 0. If D is 1 and I press the clock, then we get the 1 on the output of the LED. If I hit the reset, then the Q output of the flip-flop becomes 0. Right? So our circuit works, our Verilog circuit works in the same way that the built-in library D flip-flop circuit works. Right? We just happen to learn how to write a flip-flop that had an asynchronous reset and preset. Synchronous would mean then that we would remove these signals, the clock, or we'd remove the edge signals from the sensitivity list and not have to change anything else. In other words, if we were to do this, the only thing that could trigger or activate the circuit is the item in the sensitivity list, positive edge of the clock, and that makes reset and preset now synchronous because it's based on the clock edge triggering this. What makes it asynchronous is when we add these edges of these resets in here as well to trigger that. So it's not dependent, the circuit's not only dependent on the clock, it also activates according to these signals as well. Right. So let's try then one other thing. In a previous lesson, we had some code for a 7-segment display. I'm going to make a new Verilog file and bring this in here. All right, I'm going to go find my code for my bitwise operators. Now, I have it in several places. Let's go to here to our 7-segment exercise we created in that video. And here's the one with case statements. Open that with Notepad. Select my code. Okay. So this code drove a 7-segment display. Right, it had an enable that we could turn on, right? So to turn things on and off. And we saw when we gave it this different binary patterns, we got different information, or hexadecimal digits out on our circuit. So I'm going to add this into the project. Hex to 7-segment case. This was made with a case statement, is why I called it that. Don't seem to be copying things very well. Hex 7-seg case.v is part of the project now. All right, I want to create an instance of this in the top level. All right, remember display on. If I go ahead and hard code a 0, so what turns the display on, and let's go back here, is when the display is set to a 1, not a 0. So if I hard code that to a 1, we'll turn on a hex display. I want to connect some sort of binary value to that. And when we tested this circuit before, we were using switches. Right. So what I'm going to do is I'm just going to enable switches 3 down to 0 to connect to this. I'm going to connect to the 7-segment output hex 0. Right. And I need to define that in my list as well. So hex 0 needs to be added to the list. It's an output wire. So 6 down to 0 for all 7 segments. I need to turn on all these switches. And so for right now, I'm going to turn off this D flip-flop module. And I'm going to just go ahead and say 3 down to 0, show me the switch. Actually, you know what? I'm just going to leave that alone and turn that off right now for the red. All I want to do, and I have to give this some unique instance number, so instance 1. All right, all I want to do is show you that the hex display is working. Let's recompile. Oh, I forgot the dot. So can't connect by both order and name because I forgot the dot there. Wasn't happy about that. All right. I'm going to kill the current program on the board. All right, when this finishes, we should see a 7-segment display running. Okay, I've got the compilation successful. Bring up, thought my programmer was up, guess not. Add my SOF file, start my program. All right, so all this circuit's doing is we're going to show, I just want to remind you what that code did, right? So I've got switches as 4 binary inputs. We've got the pattern 0, 0, 0, 0, binary pattern of 4 zeros. We're seeing the hex digit 0 out here, right? If we cycle through, we'll see a 1, a 2, a 3, right? 0, 1, 0, 0 gives us a 4. 1, 0, 1 gives us a 5, 1, 1, 0 gives us a 6, 1, 1, 1 gives us a 7. Right? We cycle through to, there's A, there's 9, there's A, there's B, there's C, there's D, there's E, and then there's F as well. Hopefully you can see that. There's not too much glare. All right, that's what that hex to 7-segment display signal does. Right? It takes a 4-bit input, though, the way we wrote that circuit in order to drive something. What I want to do now is I want to drive the output of the flip-flop on here. I want to leave this display enabled, but what I want to do is I want to pass the binary value in the flip-flop output. So here, right, I was showing that on the red LED one before. I want to give that some sort of name. So I'm going to have an internal signal declaration. Right, and I'll just call that wire, and I can call that Q. Right, so I'm going to wire to Q here. This Q. Now, this Q I'm going to now use as my input to here, but notice this Q is only 1 bit, so I need to make a concatenated signal. And I do that inside curly brackets. That double quote doesn't have any place there. So 3-bit binary is 0. And if I append to that the value of Q, right, Q can be 0 or 1. So my input to my hex display will either be 4 zeros or 3 zeros and 1. Right. So now, let me just go ahead and still show our output. So we're going to see the output of our flip-flop now on the hex display. If I did everything correctly, so we have to recompile. I was complaining that I'm not driving red LED 1. Right, because I'm actually using that and I'm no longer driving it because I got rid of that. So it'd be better to say that. Stop and stop the current process. Right, because I get after you all about warnings. I'm gonna make sure that I don't have any inappropriate warnings in there. Now I've got some other stuff going on. All right, I'm trying to now reprogram the board. I left all the switches on from the previous one. All right, I'm turning all the switches off. Now our output should be based on our flip-flop output. I believe key 1 was our reset. Let me just bring that up here. Notice we then wired key 1 to reset in the Verilog. So key 1 should give us then an output of 0 from our flip-flop. So now we see the pattern 0 on there. Right, preset gives us a 1, so now we see the output here numerically. Otherwise, same way here, D's a 0. If I hit the clock button, right, my output on my flip-flop is now a 0. D's a 1, I hit the clock button, my output is now a 1. The reason I wanted to show you this is so that you could learn to work with some concatenated signals. Right, we can use LEDs to show state. It kind of makes sense to do that if we just have 1 bit, but I find the hex display is easier to read. We did that then by adding the hex to 7 segment module to our project, creating an instance of it, and we only had 1 bit to send it. Remember, this signal is defined as 4 bits, so I have to wire 4 bits to it. Right, this signal in this module, then binary value was defined as 4 bits. In order to use that, we wired 4 bits to it. We put 3 zeros out to the left of Q with a concatenation operators, right? Those curly braces there. So we made a 4-bit bus out of those bits. Right? And that's how we ended up with our display then on the hex to 7 segment. All right, so that is it for our lecture on D flip-flops and how they operate.